Welcome back. In this video, we'll introduce imaginary and complex numbers. We'll introduce the fundamental theorem of algebra. We'll determine real and complex zeros of a function, and we'll determine a function given its real and complex zeros. We know how to find the principal square root of any non-negative real number. In earlier courses, we have explored how to find the square root of a negative number. When the value of the radicand is negative, the root is said to be an imaginary number. The imaginary number I is defined as the square root of -1. So the square root of -1 equals I. Recall that you can write the square root of any negative number as a multiple of I. Consider the process of evaluating the square root of -9. So the square root of -9 then is 3i. Also, what might be helpful for us in our studies is I squared is equal to I times I, or I squared is equal to the square root of -1 times the square root of -1, or the square root of -1 squared, which is simply -1. So I squared equals -1. I encourage you to commit that to memory. A complex number is in the form of a plus bi, where a is the real part of the complex number and bi is the imaginary part. Actually, all the numbers we've been using for our entire life are part of the complex number system, but the imaginary part's always been 0, so we've only worked with the real part. But now we're adding the imaginary part as well, so when we have the real part and the imaginary part, we then see it as a complex number. And the order in which you write this matters, so you always have to do the real part to the left and the imaginary part on the right. Let's take a look at the fundamental theorem of algebra. The fundamental theorem of algebra guarantees that any polynomial function of x with real number coefficients can be factored completely over the set of complex numbers, which means any polynomial can be factored, but it might have real factors and it might have imaginary factors. Essentially, what the fundamental theorem of algebra says is that if we have a 4th degree polynomial, something like x to the 4th, there will be 4 factors. Some might be real and some might be imaginary. So that means there will also be 4 zeros. So the degree of the polynomial will be equivalent to the number of roots or zeros of that function. Keep in mind, though, that that doesn't mean you're going to see visible x-intercepts there, because some of those roots could be imaginary. A little insight into our future: the complex zeros or the imaginary zeros always come in pairs. So something to keep in mind. So sample 1 asks us to completely factor this expression x cubed minus 6x squared plus 13x. They give us a hint we're going to have complex numbers here. So I took the liberty to factor out the greatest common factor of x, leaving us with x squared minus 6x plus 13. I tried to factor that and I couldn't. There aren't any factors of 13 that add up to -6, so this isn't factorable. So now I'm going to use the quadratic formula to find out what the factors are, the x-intercepts are, and we'll back into those factors in just a minute. So our quadratic formula, our a value is 1, our b is -6, our c is 13, so we plug everything in. X equals the opposite of b, or 6, plus or minus the square root of b squared minus 4ac all over 2a. So I substituted everything into the quadratic formula. I went ahead and simplified under the square root. Be super careful with this minus sign here. So we have 36 minus 52. So under the square root, we have the square root of negative 16. There we go. We're going to have an imaginary number. So 6 plus or minus the square root of negative 16 all over 2. The square root of negative 16 is 4i. So we have 6 plus or minus 4i all over 2. I factor out the 2, and I get x values of x equals 3 plus 2i, x equals 3 minus 2i, and then our other factor here of x equals 0. So those really aren't the factors, those are the zeros, or the x-intercepts. Well, they want the factors of these, and if you think about it, the factors of a particular number. So if we had a factor, let's just pretend we had a factor of x equals 5. Well, pardon me, if we had a 0 of x equals 5. Well, that's going to come from the factor of x minus 5. So our x minus 5 is the factor that generates the 0, or the x-intercept, of x equals 5. Okay, so these are our zeros, which means 3 plus 2i comes from the factor of x minus 3 plus 2i, right? X equals 5 as a 0 comes from the factor x minus 5, so these minus signs. So x equals 3 minus 2i comes from the factor x minus the quantity 3 minus 2i. And the factor of x equals 0, well, that just comes from x. So I distribute my negative here. So I have x minus 3 minus 2i is a factor. X minus 3 plus 2i is a factor. And x is equal to my final factor. So these three are my factors. And then my zeros, again, are 3 plus 2i, 3 minus 2i, and 0. Example 2 says factor completely using complex numbers. 4x squared y plus 25y. So again, I'm going to take out the GCF of y, leaving me with y times 4x squared plus 25. In our earlier studies, we would stop here because we'd think 4x squared plus 25 is no longer factorable. Well, we can't factor it with real numbers, but we can factor it with imaginary numbers. So our difference of two squares pattern generally says we could factor this using kind of the square roots of 4x squared and the square root of 25, but without a minus sign, we couldn't do that. But we could do that, but with a plus sign, we couldn't. But now with imaginary numbers, with a plus sign, we can. So let's go ahead and take a look at this and see if we can do this. Let's call this the square root of 4x squared is just 2x, and then we have another 2x. And one is going to be plus and one is going to be minus, but the square root of 25 in real terms would be 5, but if we do this as imaginary, 5i times 5i, let's see what happens here if I FOIL this back. Okay, let's take a look at what's positive 5i times negative 5i. Well, that's going to be negative 25i squared. Well, what's I squared but negative 1? So that's negative 25 times negative 1, which is positive 25. So we actually, when we do this as a difference of two squares and use imaginary numbers, we have now factored a sum of two perfect squares, but our b term here has to be imaginary. So we have successfully factored this using complex numbers. You may also see, because they like the coefficient on x to be 1, so then we have to divide both sides by 2 here, and then we can say that's x plus 5i over 2 and x minus 5i over 2, and we have completely factored that. The conjugate root theorem says that if we have a factor a plus the square root of b as a root, then that also must come in conjugate pairs. I mentioned that earlier in the video. So whenever you have imaginary roots, you always will have pairs of imaginary roots. So if a plus the square root of b is a root, then a minus the square root of b is a root, which is about what we did in the previous one. We said the plus the square root of 25 and minus the square root of 25. So if a plus bi is a 0 of a function, then a minus bi is also a 0 of the function. So a polynomial function f of odd degree with real coefficients has at least one real 0. Well, that totally makes sense because the zeros with imaginaries come in conjugate pairs. So if you have one imaginary, you have 2. If you have 3, you have 4. So you will always have an even number of imaginary roots. Example 3 says we want to find a polynomial function of degree 5 whose coefficients are real numbers and has the zeros of x equals 2, 3i, and 1 plus I. So they've given us 3 zeros. Find the remaining zeros of the function. Well, if this thing is degree 5, we must have 5 zeros. Well, x equals 2 is one of the zeros. 3i is 1, but it comes as a conjugate pair. So our zeros are x equals 2, x equals 3i, but x could also equal minus 3i. And yes, you could write that plus or minus 3i. They give us x equals 1 plus I, and its conjugate pair is x equals 1 minus I. In example 4, they ask us to find a polynomial function of degree 4 whose coefficients are real numbers. So we're going to need 4 x-intercepts. We're going to need and it has zeros of 2, 2, and negative 3 plus I. So they gave us 3 of them. So we need the fourth one. Well, the fourth one, okay, we have zeros at 2, 2. So 2 is a multiplicity of 2. And we have negative 3 plus I. So the one we're missing is negative 3 minus I. So I found the fourth zero. Now it's asking us to find the polynomial function. So these are our zeros. So from those zeros, we can write our factors. So we'll get our factors. As we saw before, if x equals 2 is a 0, it comes from the factor x minus 2. X equals 2 is another 0, so we have another factor of x minus 2, so I can just write that as x minus 2 squared. And then we have x minus a negative 3 plus I. And we have x minus a negative 3 minus I. So notice I put that in parentheses because we're going to have to distribute that negative through. So our factors are x minus 2 squared times x plus 3 minus I times x plus 3 plus I. So I've multiplied out x minus 2 quantity squared using my pattern, x squared minus 4x plus 4. And these two I'd have to FOIL together, but if you notice here, we have x plus 3 minus I and x plus 3 plus I. Well, x plus 3 is, we could look at this as a minus b times a plus b. These two actually is a difference of two squares, so we can use our difference of two squares pattern to help us multiply that out. And in doing so, when we do that, this factor becomes x plus 3 quantity squared minus, well, I times I is I squared, so that's minus a negative 1. So I carried down my x squared minus 4x plus 4. I multiplied out the x plus 3 quantity squared. So I get x squared plus 6x plus 9. And then minus a minus 1 is plus 1, so that's going to become 10. So now that I have these two trinomial factors, I'm going to multiply those together. This might rock your world a little bit, but I'm going to line these up vertically and line up my like terms and simplify vertically. So take a look at this. So when I multiply x squared on the left here times every term in the other trinomial, x squared times x squared is x to the 4th, x squared times 6x is 6x cubed, x squared times 10 is 10x squared. Then I'm going to take the negative 4x and multiply it by all three, and I get negative 4x cubed, so I line up my x cubes. I get negative 24x squared minus 40x. Then I take the 4 and multiply it by all three, and I get 4x squared, so I line that in my x squared column, plus 24x plus 40, and I add all my like terms down, and I get my polynomial is x to the 4th plus 2x cubed minus 10x squared minus 16x plus 40. I took my function and grabbed my graphing calculator to graph it. I put this into my graphing calculator. I stole my window from the problem, and I put that window in. So my x's went from negative 5 to 5, my y's from negative 10 to 60, and then I went ahead and graphed my function. So it looks something like this. I evaluated it, finding the relative minimum, the relative maximum, the absolute minimum. I found those points using my calculator, and I went ahead and will answer that final question. So after using my calculator to find the relative mins and max, I've got a relative min at negative 2.78 and 23.95, so I plotted that point over here. I've got an absolute min and a 0 at x equals 2. I plotted that point. My y-intercept is 40. I can eyeball that, right? I put 0 in for x. Everything drops out. Our constant is our y-intercept, so that's 40. I plotted that. And then we've got a relative maximum at about negative 0.72 and 45.86. Our left and right hand behavior both go to positive infinity. They go in the same direction because it's an even degree polynomial. And since our coefficient is positive, they go in the positive direction. So now that I've got my critical points, I can go ahead and finish off my graph and get something that looks like that. And that mimics what we had on our graph. So that concludes our introduction to complex zeros and a little bit of putting it all together. And we'll get some more practice with this when I see you in class.